These are the notes on the Drake equation. A lot of people wonder, is there any other intelligent life in the universe? This is something that people try to speculate about. They try to look for evidence for, and the evidence seems to be very, very hard to come by, very minimal. Sometimes you'll have claims that there's direct evidence of this. Many of these have been shown to be fakes, and then there's several that we still do not know what they are exactly, but that doesn't mean that we can necessarily connect them to there being life elsewhere in the universe, just because there's a light in the sky that is unidentified. Okay, now they're calling them UAPs, unidentified aerial phenomenon. But what we can do, what we can really do, is we can estimate the probability based on what we do know. So we can make a pretty good estimate of how likely life would be, even without direct evidence of there being other life. This is exactly what the Drake equation tries to accomplish by taking a number of factors, some of them very large numbers, some of them fractions, and multiplying them together to try to get a ballpark estimate, kind of an educated guess, about the number of intelligent civilizations there might be in our universe. So basically, the Drake equation is a big educated guess. It's trying to predict statistically what the likely number of intelligent civilizations in the universe might be based on some numbers that we can make pretty good estimates of or actually even eventually know. So the first two numbers are the big numbers, and then the remaining numbers are fractions, numbers less than 1. They wind up reducing it, paring it down, chopping it down, and then you just sort of see what number you're left with. Okay? If the number you're left with is 1, well, that stands to reason that we have 1 right here, and so the prediction would therefore be no others. If the prediction is greater than 1, then you would expect there to be more civilizations in the universe. Okay, you can't be sure of that, but it's an educated guess, it's a speculation. And if the number is huge, then you would expect there to be quite a lot of intelligent civilizations in the universe. So the first two numbers, Ng, the number of galaxies in the universe, and N star, the number of stars in the Milky Way galaxy, are both very large numbers. The original Drake equation was limited to the Milky Way galaxy, so then we're going to go beyond that because it's pretty easy to do it and include the whole universe, because why not? After that, we get Fp, which is the fraction of stars that actually have planets. Then we have Ne, which is the fraction of planets suitable for life, or that are like the Earth. Fl, the fraction on which life actually arises. Fi, the fraction of inhabited planets on which intelligent life evolves. Fc, the fraction of those where technology develops. And then F, capital L, the fraction of a planet's lifetime with a technical civilization. So once you multiply all these numbers together, you wind up getting a result. And the better your information going in, the better your result coming out will be. And depending on what that number is, it's a prediction of how many intelligent civilizations you would expect to find in our universe. So the first number we're going to start with is a very large number, the number of galaxies in our universe. we have known this number for a while. Within reason, we have an estimate of what this number is within a certain ballpark, and that number is 100 billion. So it's not exactly 100 billion, but it's definitely in that ballpark. This is ng, the number of galaxies in the universe. Next, we need to know the number of stars in each galaxy. Well, as you know, we are in the Milky Way galaxy. We are in the spiral arms, so that's why we don't see it like this. The Milky Way galaxy is a very typical average galaxy, and the number of stars that the Milky Way galaxy has can be used for the number of stars in an average galaxy, and that happens to be 100 billion. So n star, the number of stars in each galaxy, is also 100 billion. So those are two very large numbers. That's going to start us off, and after that, all the other numbers are only going to pare it down. By the way, if we do encounter any alien life, it'd be interesting how we overcome the communication problem, because it would not be so easy to communicate with a life form that evolved in a totally different environment. How would they communicate? Would they even use sounds? In science fiction, they usually have alien life forms with 2 arms, 2 legs, even though they might look very different from people. Basically, they're very humanoid, and that's just because we usually throw someone in a costume. It just makes it easier. But there's no reason to expect that they would necessarily be so similar to humans. And communicating with them could be a major issue. So hopefully, if we do find any alien civilizations, hopefully we can get along with them. Hopefully discovering them doesn't lead to major problems and endless warfare, but who knows? Kapla. So how many stars are like our sun? Well, it turns out that our sun is not a very unusual type of star. Our sun is a G-class main sequence star, and about 1 out of 10 stars are roughly similar to our sun. It's a very typical kind of star. There's plenty of them. In fact, the very closest star to us is actually a group of 3, and one of them is almost the same as our sun. So right away, if you travel out, try to find the next closest star, and one of the 3 there is just like the sun you just left behind. So this is Fs, the fraction of stars like our sun. 10%, which of course is 1 over 10, 1/10, is the fraction, or 0.1. Lack of communication could lead to all kinds of problems. Maybe we'll discover alien civilizations that are already at war with each other. Yikes, do we really want to get involved in that? I don't know. So how many sun-like stars have planets? This is something we are discovering all the time, as we are discovering what they call exoplanets, planets around other stars, not in our solar system. And we're getting new information about this all the time. We're increasingly finding planets around stars where it seemed unlikely. For years and years, people would refuse to speculate on this particular point. The presumption that people usually had in the past was that stars did not have planets, which I always thought was strange, because if you look at our solar system, well, it clearly does have planets. So then why would you presume that other stars that we can't see as closely, can't see what's right around them, would not? It seems like, if anything, our presumption should have been that they do. So at this point, we're narrowing it down, but it could be about half, about 50% or more likely to be more. Now, the reason that it's not every star is because many stars, in fact, most stars, are in binary systems. And it turns out that it makes it difficult to have stable orbits of large planets at a great distance from the star or in medium distances from the star if you're in a binary system. You can have orbits that are close to one of the stars or far out from the two of them. So we're still learning about that. But FP, the fraction of stars that have planets, for now, we can use 1/2, 0.5. So we're doing all that discovery with the most modern advanced telescopes we have, both on the Earth and in outer space. This is the Keck telescope on Mauna Kea in Hawaii. People think Hawaii is nice and warm. Well, not if you're up at 14,000 feet. It's not. It's pretty cold up there. And the air is very clear. They're above a lot of the atmosphere. And that's why they like to put telescopes on mountaintops, like, Mount Wilson in LA and Mount Palomar in San Diego. They like to put telescopes up on mountaintops because they're above a lot of the air and they don't get as much light from all those pesky people that live around here. Speaking of intelligent life, right? So then the question is, even if you have planets, how many of those are going to be planets that are like the Earth? How many of those planets are Earth-like? So we are really learning a lot about this now with all the recent measurements of exoplanets, and they're getting a much better idea. But for years, we had to base it on our own solar system. And so far, the number hasn't deviated very far from that. We'll see what happens in the future. But basically, if you look at our solar system, we've got 8 planets, and one of them is like the Earth. You could make arguments that a few of them have some Earth-like qualities, but none of them are really like the Earth. This is Ne, the fraction of planets suitable for life. So in our solar system, it's about 1 in 8. It could be a little bit more or a little bit less than that. So that is pretty close to 1/10, 1 in 10. So we could also use that in our calculation. Okay. Of course, Venus is our sister planet, so in many ways it's like the Earth, but it does not appear suitable for life. And so they look for planets that are in what we call the habitable zone, where you could potentially have liquid water on the surface. That's the big issue, people suppose, although we're really not sure about that. That's just a presumption we're making. So just based on the solar system we know very, very well and don't have to speculate about, okay, it's 1 in 8. If we ever did encounter alien civilizations, we probably could not crossbreed with them. Okay, like for example, Mr. Spock in Star Trek. A lot of people forget that he's not Vulcan, he's half Vulcan. His mother was a human. So would that be possible? No. I could pretty much definitively say no, because they're just different species. Not even just different species. They're not even in the same family, the same order, So basically, being that distantly related makes it impossible to have hybridization. The only times you can get hybridization between different species is when they're very, very closely related. They're in the same family, like when you have a lion and a tiger making the liger. But then the offspring, the liger itself, can no longer reproduce. And if you get even more distant than that, it just never works. It just doesn't happen. So it's just not going to be possible, like they have in science fiction shows, that you would have aliens and humans mating, having offspring. Would not happen. Then, if you wonder about how long has complex life been on the Earth? Well, if we are very loose about the term complex life, like multicellular, like organisms that had more than one cell or that had anything complex about them, like tentacles or eyes or anything like that, pretty much that kind of life has only been on the Earth for about 600 million years since the Cambrian explosion. Okay? Which turns out to be, if the Earth is about 4.6 billion years old, or maybe 4.55 to be more precise, 600 million years is about 1/7 of the age of the Earth. Now, you might argue that, well, that's not intelligent life. Just because a creature is swimming in the ocean doesn't make it intelligent life, but I'm trying to be generous here because I think it'd be interesting to discover any life. Okay, it doesn't have to necessarily be just like us, but any sort of complex life. And then there's some other factors in this equation which pare this down. So the fraction, if the Earth has had life for 1/7 of its age, then you could imagine that, well, if you were to come across the Earth in its distant past, you would not have found life. You would not have found anything more than possibly just single-celled bacteria. So if we look at it this way, you would have to arrive at the Earth at this point in time in its development. What if you're talking about a period in time when the Earth had just formed? You wouldn't find life. And what if we find another planet in the universe almost exactly identical to the Earth, but earlier on in its development? See what I mean? So using this as a predictor of that, even if a planet is like the Earth, you still will only find life on it about 1/7 of the time. 1/7 of the fraction of its age. See what I'm saying here? So again, this might not be representative of every Earth-like planet, but this is the only planet that we have good information for. So this can pare down even the Earth-like planets if we find them at the wrong stage of development, might not have life. Get it? So if we multiply the two big numbers together, 100 billion times 100 billion, we get a number that we often write in scientific notation because nobody wants to say 10 sextillion. So we call it 10 to the 22nd stars in the universe. That's our starting point. That's our biggest number. You could also write that as 1 times 10 to the 22nd stars in the universe. After that, you multiply it by the various fractions, and it shrinks the number down. 1/10 are sun-like, 1/2 of those have planets, 1/8 of those are Earth-like. And what you wind up getting with all these fractions is it really reduces the number quite a lot. You're basically dividing by 160 just from those factors alone. The only problem is the number we started at was so huge, we'll still have a lot left over. So if we take the number of stars in the Milky Way galaxy, this is just within one galaxy, and then we divide it by 10 to get the ones that are like the sun. We divide that by 2 to get the number that have planets. And then we divide that by 8 to get the number that are like the Earth. Then we divide that by the fraction on which life has developed, advanced life has developed. And finally, we narrow it down to the percentage of time that humans have been around and had the ability to produce signals, because what the Drake equation was really trying to calculate was whether we would actually detect evidence of other life using radio signals, which seems to be the only plausible way of communicating at great distances in the universe. So using these rough numbers, what we would wind up with is a number of about 9. And so you might say, oh, 9 is pretty good. 9 civilizations at this moment in our galaxy. And of course, this number would be much, much larger if I had started with the bigger number of the stars in the universe, of course. But then again, you got to remember how big our galaxy is. If our galaxy is 100,000 light years across, and there's 9 civilizations sort of sprinkled around it and we're one of them, the chances of us being close enough to one of those other civilizations to actually receive a signal in the lifespan of human civilization turns out to be not so good. So if the number is only 9, it wouldn't be surprising if we never find evidence of other intelligent life in the universe. If the number turns out to be larger than that, let's say we made a miscalculation, let's say it winds up being more like 1,000, well then our chances of course are much better. But if the number winds up being a single-digit number like that, then our odds are a little iffy. Remember the Milky Way galaxy, okay, we are in the spiral arms. If there just happens to be one nearby, then we might detect it. If it's on the other side of the galaxy, then it might take 100,000 years for their signal to reach us. In fact, if we do get a signal from another alien civilization, that civilization could be long gone for all we know because of the delay time of the speed of light. Also remember that our galaxy is a barred spiral, and that's the way to remember it. Think of the Milky Way candy bar. So it's interesting to wonder, is there any other life in the universe? The Drake equation does not really answer this question, but it takes a stab at it. It makes an educated guess. Okay, thank you.